My name is Dan Caesar. I manage our Bluehill product portfolio. So that's a software application that we use here at Instron to operate our test frames. And today, our session is going to focus on data capture rate. So data capture rate is one of the most important parameters to be very familiar with and be very aware of how you've set that up in your test to make sure we have the proper amount of data captured to make sure our calculations are exactly as we expect them to be. So we're going to switch over to a couple slides just to introduce the idea of data capture rate, make sure we're all on the same page before I dive a little bit into our software application, Bluehill Universal. So everyone can see the system that's shown in front of us here, that we have a Instron electromechanical single column frame. And it's a little bit hard to see, but there is a blue plastic specimen that's in between these two wedge grips. There's also a clip-on extensometer attached to that specimen, and we use clip-ons here at Instron to measure the deformation, essentially the change in displacement of that plastic specimen or any other material you might be testing. And then on the right here is our all-in-one computer, where you can see just a snapshot of maybe a test curve. You might have force on the y-axis and displacement or strain on the x-axis, where we're actually graphing and displaying the data that's being captured by the system. And so really how does the data capture play into this system? That first, we have physical events that are actually occurring. So the specimen itself, that blue plastic specimen, as it's being pulled apart by our frame, that we have load increasing, that there's deformation happening, there's physical events that are actually occurring to that particular material. But we need to capture those physical events. And so the way that we do that is that we have different sensors. So for instance, that clip-on extensometer that I'm pointing to here is capturing those physical events and actually converting them into an electrical signal. So you might have other sensors, you might have a load cell or other things that are capturing force or other measurements that are required for your testing. So all of these are kind of observing, capturing these physical events that are happening to your specimen and converting them into an electrical signal that will then be processed. And so that electrical signal is then converted, filtered into digital data that we can actually see visually represented in this test curve in our software. And that digital data is then being used to perform different calculations that you might have required for your particular test application. And why is this actually important? So that data capture rate, the rate of data capture for that digital data that we're talking about, how many points per second is the system actually capturing? It's a very crucial parameter, and it's what we're going to be talking about today. And it's important for a couple of different reasons. So kind of the two sides of the coin are that if we're too slow, if we have too slow of a data capture rate, then we actually might be missing these physical events. And then the flip side is that if we have too fast of a rate, if we have collecting just an enormous amount of data points for your test, that it just is completely unnecessary. We might be creating this massive file that might bog down the system, might be difficult to store if you're running dozens of tests per day. So we really need to find this healthy balance between having a too slow and too fast data rate to make sure that your test has been set up properly. So just to show a symptom of this, I want to kind of take this one step further, kind of exaggerate this oh no, too slow data rate case. And so we have this actual event. So this might be a test curve that's produced maybe in a appeal test, something that has a lot of peaks and troughs to that particular data. And this might be the physical deformation kind of force displacement curve for that sample. But that could translate into this. It could translate into the software as a curve that is displayed such as this. So how does that actually happen? That if we represent each data point collected as maybe one of these stars, and we actually apply that to the physical events that are occurring, and we draw the points, the line between those, all of those data points that are being collected, what do we get? We get this red line. So it's just a direct translation. And why is that a problem? That if we kind of overlap these, it becomes very clear that there are certain peaks or certain troughs, certain regions of data that the user is entirely unaware of, that any calculations that you might be relying on are completely omitting because of the data rate being captured a little bit too slowly. So, of course, that's a situation that we want to avoid. So to try to position ourselves where we are setting up test parameters properly, there's a few tips that we want to live by when it comes to data capture rate. And so first and foremost, that we really want to have a good understanding of the nature or the speed of these events that are happening. So is this a gradual transition? Is it a very sharp spike? So generally, are things happening slowly or quickly? And for each of those events that we're concerned with, that we want to make sure that we have about 10 to 50 points to be able to properly characterize that particular event. So if we're very focused at the break event at the end of a test, it could be happening in just the fraction of a second, that we want to make sure that we have those 10 to 50 points in that fraction of a second to make sure that we can properly characterize that break. Or if you're maybe at the very beginning of a test and you're trying to determine the stiffness or the modulus of your plastic or your metal or your composite, whatever you're testing, that a lot of those events and those regions of interest are happening incredibly quickly. So it could happen in the first second or two of the test, and we want to make sure that there is a proper amount of data being collected in those particular regions. So the third tip here, we're introducing the idea of bandwidth. So when we're talking about data capture rate, which I'm focusing on today, it's kind of it's part of the bigger family of just data acquisition in an Instron system. Another part of that is bandwidth, which is really it's one step closer to that physical event. So it's really characterized as the responsiveness of your electronics when we're converting those physical events to that electrical signal. And it's something that is many times designed into those sensors, designed into your system, something that the user has limited capabilities of changing. So we just need to be aware of what it actually is set to. And if you can change it, that might be an option for you. But at least the tip is to make sure that your data rate is 2 to 10 times higher than your sensor's bandwidth. And then lastly, last tip here is don't forget to be very familiar with the test standard. If you are testing to a particular ASTM or ISO testing standard, that many times that's a very good place to go immediately to try to find any guidance. So for instance, D638, very common plastics testing standard, that there's a section or a method within that test standard when you're trying to characterize the material's Poisson's ratio. And if you're running that type of test on your piece of plastic, that it's recommending specifically to have at least 20 points captured per second. But it's actually saying that you should have more if possible. So of course, it's dependent on the type of system that you're using, whether it can capture more or less than what's recommended, but that's something that you need to be very aware of, not just because we want to make sure our calculations are as accurate as possible, of course, but in this case, you're actually going to be not in compliance with the standard if you're only testing at 10 points per second for Poisson's ratio. And the last thing we're going to look at before we jump into the software is just some default values that our Instron electromechanical systems use. So our 33 and 5900 systems are prior low and high tier electromechanical systems. And then in addition, our current platforms, our 3400 systems and our 6800 electromechanical systems, that there's default values that if you go and create a test method, that our default data rate is going to be 50 hertz or 50 points per second. So hertz is the unit that we like to use to understand how many points per second are being captured. You might see that as represented in time. So 50 hertz is 20 milliseconds. You could say every 20 milliseconds, data is being captured by default for our test methods. And then the system's default bandwidth is 10 hertz. And so I have that asterisk on the data rate because for our higher tier systems, so previously our 5900s, currently our 6800 systems, that they by default capture more than just time-based data. So they by default actually capture intervals at 0.25% of your load cell's capacity. So that is just another criteria when it is satisfied that your system will then capture data points in addition to that time-based 50 hertz. And so I might spend a little bit of time of actually why having that additional flexibility is important and why it's valuable. But at this point, I think we're going to be jumping into Bluehill, where I have some samples that have already been tested. And so before I jump into the software, I can actually show you the material that we were running, and it was a peel test. So I have a piece of tape and adhesive, and essentially what you'll see is the curves that are the result of 3 tests, where essentially the machine is gripping the upper and lower part of the piece of tape, pulling it apart. And that will generate the curves that we're going to look at, where we have quite a bit of peaks or troughs depending on how that adhesive is behaving on the 2 substrates. So I am now going to open up Bluehill Universal. And this, if you're not familiar, the slide before had Bluehill Universal in portrait, which is how we typically sell and how our customers are using Bluehill Universal on our touch screens that are mounted directly to our Instron frames. You can actually kind of see a couple of them behind me. For the sake of this demonstration, we're in landscape, obviously. So I'm using my own computer. So we're in landscape here. And we're looking at the test workspace. And so you can see that I've run 3 specimens, and I've set up a workspace that shows those tests one at a time. And I'm looking at force on the y-axis and displacement on the x-axis. And I actually have an average value calculation that's occurring, which is this band that you see. But the data is of course the jaggedy line behind that. I'm also showing some raw data, and I have that result of that average value calculation right here. So one thing I just wanted to quickly show is the difference between these 3 tests, because what I did to try to demonstrate the effect of data collection is I ran 3 identical specimens at different data rates. So the first specimen I ran at our default data rate, which is every 20 milliseconds, which is 50 points a second or 50 hertz. And we produce this curve. If I go to our second specimen, I reduced that data rate from our default, so 50 points a second, to 2 points a second, or 2 hertz. So immediately you can see you can almost see the individual lines that are being drawn in between each of the data points, that we see a clear difference between those two curves. And then for the third sample, I did the opposite, and I did a lot of data. And so it looks kind of similar to the first test, right? It's hard to really, without comparing them right next to each other, it looks relatively similar. I used 1,000 hertz, 1,000 points a second for this particular sample. So it's actually 20 times more data than the first. And one of the little tricks that I want to show that because as of right now, each of these curves, these are simply just the lines that are being drawn in between all the data points. But if you want to actually visualize each data point and have that appear on the curve for you to evaluate whether or not we think there's enough for each of these events, that the way that we want to do that is by editing our graph properties, which we can edit with this little pencil. And so we get this dialog that pops up, and we want to go into the advanced menu of the graph properties, and we'll go down to the plot itself. So if you're only graphing one specimen per graph, you're going to see just plot 1. If you have 5 specimens per graph, then you'd see plots 1, 2, 3, 4, 5, where you can stylize it. You can change the color or the thickness of the line if you so choose. But one of the options is this symbol option, which allows you to choose. So it's, by default, it's set to none. But if you want to visualize those data points, you can set it to dot or a different shape if you prefer. And now if we look at that same curve, I've graphed those points in blue. And so again, this is the first specimen. It's graphed. You can see quite a few data points, but it's very easy to see each of them. If I go to the second specimen, all of a sudden the curve looks quite a bit less blue because there's actually quite a bit less data being collected. So I can zoom into any part of this, and there's a little blue dot kind of with lines drawn in between them. So it's a very clear way of understanding how your data rate is actually leading to the curve that's being produced. And any underlying calculations that you're using are using those that data. If I go to the third, we're going to see basically a solid blue line, because there is so much data. I can even zoom in to some of these regions, and it's almost still solid blue because of how many data points are being collected. So another way of easily demonstrating that is if we look at the data viewer, in this test that might have taken 20 seconds, I think I was running it at 500 millimeters per minute. In this third specimen where I was capturing 1,000 points per second, that there was almost 26,000 data points collected in that time period. And if we look at any of these individual events, that 10 to 50 rule is certainly not, we're certainly exceeded. So definitely unnecessary amount of data for this particular type of test. Whereas if we go to maybe the first sample and we did the same evaluation, we could try to see if we have that 10 to 50 data points, which seems to be certainly much more in that realm. So the default value here is actually pretty appropriate. But that's not to say maybe the very, very end of the peel, which is not part of this average value calculation, but maybe that's something that you're concerned with as it separates, as both of the substrates separate from each other, that's actually happening in this very sharp event, that even though I was calculating things at 1,000 points per second, now we start to see individual data points. But even still here, that seems like almost too much data. But a little bit more appropriate if you were very worried or very concerned and were pointedly trying to determine that final part of the test. So that's a little bit of a trick just to enable that advanced plot one symbol as a dot or any other thing that I can disable it, it goes away. But just certainly an option as you're trying to vet the your test method that you've configured to make sure that it is appropriate. And if you need to change things, we do that in our method tab. But to actually demonstrate that fully, I just want to delete these specimens because you can't actively change some of the fundamental data capturing parameters after you've started the sample. So I just want to quickly get rid of these 3 specimens. And last one. Okay, and if I go to our method, that we have the data capture rate in our test control, and it's in the data section of test control. And so this is showing kind of the last setting that I had where that third test was run at 1 millisecond time intervals, which produces 1,000 points a second, which was a custom setting. So again, not the default. But if I go back to the default, that we see our 20 milliseconds, which is our 50 hertz. And then that secondary criteria of force. So if we do need to deviate from those default values because of what you're seeing in your curve and maybe some questionable results, maybe they're not actually calculating, or maybe you're questioning them, that you can come in and edit these to be whatever you desire. And on a 59 and 6800 system, you'll see all of the different measurement channels that you're able to specify a particular interval to have a data point being captured. If you have a 3400 system, then you're going to be you're going to have a single option, and that's going to be a time-based item. And so the last thing I'll kind of describe is why does it really matter? Why does it matter that you have these additional criteria where you can specify different measurements for your data capture? It's that you can make your method a little bit smarter. You can capture data in a couple of different ways to represent the test that's actually happening. So if you were to envision a standard tensile test where we have an initial rise in our slope, so we have our stiffness coming up, and then generally it'll plateau, and then we're going to break. That the first part of the test, we have a lot of change in force. So maybe we want to make sure we have enough data so we could have some sort of interval triggered by force for that initial rise in force. But then we start plateauing, and there's not a whole lot of change in force. And now all of a sudden, we are using our time constant to get those data points, because if we relied strictly on force, we might not collect that much data. So it's a way of collecting maybe a lot of data in that initial section when you need it appropriately. And then on the tail end of the test, that might be 75% of the actual time of the test, we're not collecting that same amount. So we kind of limit the file size. We capture the data that we need to capture in the region that it's occurring. So I see that we have some questions coming in. And so I want to address some of these at this time. So I see we have one question about maximum data rate. So the maximum data rate that is possible, so that's going to be dependent on your system. So for our current offering, we have, for our electromechanical systems, at least that's my expertise, that's what I'm going to be answering this about. For our 3400 systems that we max out at 1 kilohertz, 1,000 points a second. For our higher tier systems, they start at 2.5 kilohertz, and you can have an advanced option to allow you to actually capture 5 kilohertz, 5,000 points a second. But what I want to add to that is that, yes, maybe there are some situations where you want to have an incredible amount of data captured. But in reality, that 99% of applications, you do not need anywhere near close to that much data. So you saw in the test that I'm running here, that was 1,000 points a second. And that was a type of application, a peel test, where we need a pretty high data rate to capture and properly characterize those peaks and troughs. And 1,000 was almost 20 times more data than we really need. So now picturing, oh, I want 5,000. It's very unnecessary for that type of application, and it is there's very few and far between reasons why you'd actually need that really high data capture rate. All right, let's get another one. So I see, can you change the rate? Can you change the data capture rate in the middle of the test? So that is, yes, something that you can do. So one way that is kind of standard and built in is what I had just shown with setting different measurement sources as the different criteria for triggering the different data capture rates at different points in the test. But that's kind of up to what happens in the material. Another way of doing it is if you have our test profiler module. So it's a purchasable add-on for Bluehill Universal. That test profiler, you create a series of blocks, different sequences where you're doing different things, different machine control in each of those steps. And in each of the steps, you can specify if I want to capture any data, if I want to capture at a certain rate, or if I want at the default, or if I want to do a custom rate, that you can customize the data capture for each of those steps. So you could be doing a lot of preconditioning that might take 5 or 10 minutes, and you don't want to capture any data to save on your file size, but then you might have a step that takes 5 seconds after all of that where you want to capture a lot of data. And so that would be a way that you could change it in the middle of the test. And then the last question that I really see here that I'd like to address today is a time-based question. So if you have a test, a very long test, it takes 2 to 3 hours, what would you recommend to do? So again, number one recommendation, let's look at that test standard. So that length of a test, we might be holding a particular displacement for quite a bit of time and seeing how our load changes, or maybe you're holding a force and you're trying to see how displacement's changing as you hold that force on your material. But look at those applications, seeing if there's those testing standards, and obviously see if they say, I need to capture it once a minute, once every 5 minutes. That a lot of times those creep or relaxation tests that I described will actually tell you data collection rates. But yes, if you have a 2 to 3 hour test, that likely you shouldn't be capturing things, data points multiple times a second, that you could afford to have it every 5 seconds, every 30 seconds, every minute, depending on really what are the calculations you're trying to get out of that test. So I think that answers the questions that I see that people have posted from the chat. So I think we have to close out a slide promoting our next session that's running next month. And so I'll say goodbye for today, and I hope to see you all again.